So let's just recall the setting that we're in. So actually, before we do that, I just want to briefly mention something from last time. So last time I talked about diagonals of kernels, and I made a bit of a pig's breakfast out of it because I didn't really say clearly what I was wanting to talk about. So it's really, I wanted to talk about diagonals of Schwartz kernels and kernels and traces. Okay, so it was really in the context of traces that I was saying what I was saying last time, right? So let's suppose that we have a Schwartz kernel, so we can write tk u at x as the integral of this kernel k x y uy d mu y. And we further suppose that we have a eigen decomposition of this, right? So this is really now going to be k lambda. So, okay, I should say that k xy can be written as k lambda phi y star phi x, lambda. These are the eigen sections. So what we really want to talk about are traces of this, right? So recall that, so if we assume that the operator has a trace, we recall that the trace of tk of u is, or sorry, there's no u there. The trace of tk is precisely equal to the sum over lambda. Well, we can choose, so if we have a orthogonal, or if we have the spectral decomposition with respect to the operator tk, then we can, or if we have such a decomposition, we can write the kernels in terms of eigenbases of this form, then we can just choose that as the basis for which we evaluate the trace, because the trace is independent of the bases, right? So this is just going to be tk of phi lambda, and so now let's write this out more precisely. So this is going to be the sum over the integral of k x y phi lambda y phi lambda. Oops, I should put a d mu in here. Okay, d mu y. But what is this? So this is precisely now going to be equal to the integral of k lambda. Sorry, I should put omega here. So because it's a lambda, and then I have the phi omega of y star now acting on the phi lambda of y, d mu y, d omega, I'll just put dot here because that's the variable in which we're evaluating this in the inner product, phi lambda. So then we have the sum over lambda, so I'm assuming a summation convention in here, of course. And what do we have? So we can take, so what is this exactly? So this is going to be k omega, and then this precisely is just phi omega phi lambda, and again we have phi lambda here, phi lambda. So this is now going to be equal to lambda k omega phi lambda phi lambda phi lambda. Good. So okay, so what? Okay, maybe actually it's not better to write it in this form. Sorry, let me not write it in this form. Let me write it more instructively as follows. So let me write this as, so as I said, this is precisely going to be h omega. So I'll move the integral sign here. H, the metric acting on phi of y phi lambda of y d mu of y. So this is just going to be equal to just the modulus of phi lambda, because we've picked an orthogonal basis, right? Okay, so phi lambda, phi lambda. K omega is the eigen expansion of the kernel. Yes. So now what we have here is K omega, and this is now going to be just the integral of phi lambda. So this is going to now turn back into a lambda because of this condition. So we have this d mu, sorry, this is squared y, d mu y, and then we have phi lambda here independently. So this is just equal to 1 because it's an orthogonal basis, right? So what we have exactly here is that this is equal to K lambda, and of course this integral is also equal to 1, right? But I want to write it in this way for the following reason. So what is this? So if we now take the kernel kxy, and then we look at, so this is equal to, I'll write it again, phi lambda star y tensor phi lambda x, and I take a trace of this, right? So, okay, maybe I could have actually just written this, sorry, maybe I could have written this without this, right? So this also integrates to 1, right? So this shows us exactly what the so yeah, I could have ignored it. I could have just written that. Now let's just take the trace of this, right? So what's the trace of the kernel at xx? So that's going to be K lambda trace of phi lambda x tensor phi lambda of x, and so the trace here is simply going to be K lambda trace K lambda of so there's a sum here still, so this is going to be phi x star eating up phi x. Good. So this is now going to be the modulus phi lambda of x squared, right, with respect to this metric h. So the point is that if we now integrate the trace, so we integrate this trace of kxx, then this is just going to be the sum. So there's an implied sum in here. And this is just exactly going to be equal to lambda, K lambda. And this was, of course, just a trace of the operator tk, right? So what I wanted to say last time when I was talking about the diagonal was really that we're taking a trace of the diagonal, okay? So I'm sorry if that caused a bit of confusion. It actually caused me confusion when I was trying to write some things because I hadn't written that out nicely. Okay, so let's get back to the problem at hand now that we have all of these tools. So the first thing is that let's recall the setup. So we're on the cylinder, so we're on the infinite cylinder, and we have d naught equals dt plus a, and a is self-adjoint, adapted, it's a self-adjoint adapted boundary operator, right? So now remember we had the APS boundary condition, which we define as the spectral cut of the minus of the a little a of h half partial me. Sorry, it's maybe I should just write partial me, where the a was equal to a half of the minimum of the eigenvalues -1 and the 1, right? So the modulus of these eigenvalues. Okay, so this is what we have. And then we define the two Laplacians. So we define So now this gives, of course, this yields the operators d naught APS, which is equal to d naught. We write BAPSA. So just for shorthand, we write this APS, and then the adjoint boundary condition APS. So the adjoint boundary condition is going to be what? This is equal to the or the negative of this adjoint. So the negative multiplied by this adjoint boundary condition is just going to be the positive eigenspaces. Okay, so these are, I should have said here that these are the negative eigenspaces of. Okay, so these are the negative eigenspaces of the operator. Right, that's what this is precisely. And when we make the cut in this way, this is precisely going to be the lambda strictly negative, and it's the orthogonal sum of the eigenspaces of A. And now these are the non-negative eigenspaces of A. Well, intersect H half. Sorry, intersect H half. This is intersect H half. Good. Now we recall we considered the two Laplacians. So the first Laplacian was where we look at d naught APS star d naught APS. And then the second Laplacian we defined was d naught APS star d naught APS. So actually the reason that we consider these two Laplacians is I hope that you have covered some index theory at some point. So if you're looking at the index theorem for the non-boundary case, typically one considers these two Laplacians and compares the difference between these Laplacians to obtain an index formula, right? Or the heat kernels of these Laplacians, actually. So, so what we want to do is we want to study the traces of the heat kernels of this and or the study the difference, right? So so maybe let me say that. So from ansatz from index theory for closed manifolds, study the trace of e to the minus tau that's true. They need to be different. And trace e to the minus tau Laplace 2. Right? So, I mean, the reason we do that is because, remember, this is the index. Okay? So this is the index from the theorem that we had before. If these are trace class operators, then this is the index. Okay. So let's analyze lambda 1. Right? So the perspective that we're taking is we want to so maybe I should say something here. So we consider, so first consider, so L2 of ZE, which is what? Which is actually just the L2. We can view this as an L2 valued Banach space. And because of this equality, what we obtain is that, and so when U is in L2ZE, E, we have this expansion UTX. We can expand this in the cylinder by the spectrum of the operator A in the following way. Okay? So if we were on just the boundary, of course, this u lambda will be independent of t, because that's t equals to 0, right? That's just the usual Fourier expansion. So we really see, I mean, this is the advantage of being on the cylinder. We can make all of these identifications, and we have this very nice expression for the Fourier expansion with respect to the operator A. All right. So now let's analyze the operator lambda 1, right? So analysis of lambda 1. So what is lambda 1? So lambda 1 is going to be equal to negative partial t plus a, partial t plus a, which is equal to negative partial t squared, partial t a plus a partial t plus a squared. But now we're in a happy situation because the middle terms cancel, right? Because the a and the partial t commute. So this is just going to be negative partial t squared plus a squared. So that's the equation that we're looking at. And what's the domain? The domain of the Laplacian when we're writing it in this way is precisely going to be the u in dom d naught APS, such that d naught APS of u is in dom d naught APS adjoint, right? So okay, so we want to let's now consider this in terms of the eigen expansion, right? So let ut equals to ut lambda phi lambda in dom d naught APS. So what does it mean for u to be in dom d naught APS, right? So well, maybe let me take this out. So u in dom d naught APS is if and only if the u lambda at 0 is 0 whenever lambda is positive, right? Because for us to be in d naught APS, I mean, this is the boundary condition, right? The boundary condition that we're looking at are just the projection to the negative spectral subspaces of A. So if we're in dom d naught APS, then it means that the positive parts have to be 0. And now let's consider the action of this so we want to also consider what it means for d naught APS of u to be in the domain of the adjoint, right? So d naught APS u, so in terms of this basis, is equal to, maybe I'll write t, so this is equal to partial t plus a acting on some lambda u lambda phi lambda, so there's a t here, of course, of x. So then this, so I mean, because we've got an eigenbasis here and the u's commute through the a, this is precisely let me see. Sorry, I shouldn't write. Yeah. So this is precisely now. So I can commute the a through all of this, and I can obtain that this is the same thing as dt plus lambda u lambda phi lambda. Well, I've written an x in there, so maybe I'll get rid of the x, right? Phi lambda of t by lambda. Okay, so of course there's x's in there, but we can ignore that. Okay, so this is what it looks like. So then, so what does it mean? So that now we can explore the second condition, right? So then d naught APS u in dom d naught APS star. So what does this mean? This is precisely saying that dt plus, okay, yep. Here, it's nothing. Yeah. Okay, so what we get now from this is that dt plus lambda u lambda, I keep seeming to look right. So because I'm including the summation signs, maybe I can lower the indices, right? It doesn't really matter, but okay. So I have u lambda. So this has to now be 0 for lambda negative. Okay, because what does it mean to be in dom d naught star APS? Well, it's exactly this, right? It's really the annihilated subspace of the B APS of A. So that means that I'm projecting to just the positive eigenspaces, and therefore only the negative ones are going to be valid. The rest are going to be so the positive ones, the positive spectral subspaces take a value, but the negative ones, the negative ones are 0 and the positive ones take some value, right? So we have now two complementary conditions here, right? So we have, okay, so what do we have then? Therefore, we can write this domain in terms of the Fourier decomposition, right? So this is the U dom. So in general, we're going to be in the maximal domain of the square of this operator, because I'm looking at, well, not the square, but max, such that u lambda equals 0 when lambda is positive, and dt minus plus lambda u lambda equals 0 when lambda is negative. Okay, that's the domain of my operator. Okay, now let's consider the heat equation, right? So we want to get to the heat traces. So now let's consider so the T here in the Roman letters is the is going to be for us the transversal direction, right? This is not time. So for us, time is going to be the tau parameter, right? So consider heat equation. So the heat equation is d tau plus lambda 1 u equals to 0 with u0 equals 0, say, right? Or u0 equals u little naught. Okay. So what? So now let's expand this again in terms of this eigenbasis. So what do we have here? So this is going to be 0, which is partial t plus lambda 1, and now we have to deal with three parameters, right? So we have the heat parameter here, which is in the tau variable, So we have the tau here, we have the t. Because the t variable is the transversal variable, right? So we're looking in the cylinder now. So in the cylinder, this is t, it's the transversal, this is x. But now we're looking at the heat equation, which is a direction on top of this object. Okay, so this is why we have a tau and a t. So these are the spatial variables, and this is the time. All right, so let's expand this in terms of this equation. So what's this going to be? This is going to be the Fourier expansion partial tau minus dt squared plus lambda, and now we have an expansion here, tau t phi lambda x. Okay, this is what we have. Okay, good. So this is if and only if. So this happens if and only if. There's a 0 there. We have that partial t minus dt squared minus plus lambda. U lambda tau t is 0, and U lambda 0 in this variable is equal to some U lambda naught, right, of that variable. Okay. Okay. So if we have now a solution to the heat equation, right? So if we have such a solution to the heat equation, then we know that we're going to also be in the domain of the Laplacian, right? So if U equals U, so U tau t x equals some U tau t x solves heat equation, then what do we have? Then we have that U is in the domain, so U, it's parameterized, right? So U tau is in the domain of Laplace 1 because we're taking the exponential map, right? This is really taking the exponential map of the, I mean, we can always write a heat equation uniquely as the exponential map acting on the initial data. So we know then that we're going to not only are we in the domains of lambda 1, but to all powers of the domains of lambda 1, right? But in particular, so when tau is positive, so let's apply this Fourier expansion now, right? So it means that U lambda tau is 0 for all lambda positive. Well, I won't put all, I'll just put lambda positive. And we have partial t plus lambda U lambda tau is 0 when lambda is negative, right? This is just what we, okay, so this is cheating. I should really put a t here, and this is at t equals 0, right? So we first apply the equation in t, and then we take the t at 0, right? So this is nothing but just what we computed here as what the domain of, what it means to be in the domain of lambda 1, right? So we've done really nothing there except that. Yes? It's so which can you repeat that again, please? Sorry. Aha, because we just want to expand. So what is lambda 1? Lambda 1 is negative dt squared plus a squared. You're right. That should be lambda squared, sorry. Thank you. Thanks for pointing that out. There's a slight error here. So where is it? It's here. Yes, that's a lambda squared. That's completely true. But for the boundary condition here, it's just a lambda. Okay, good. Thanks for that. Yes, that's a bit of an error. Okay. So all right. So let k fix any number that's a real number, and let's set something. So k1 tilde lambda tau t prime. Let's set this to be the following: e to the minus lambda squared tau on square root 4 pi t. Tau. E to the minus t prime squared on 4 tau minus e to the minus t plus t prime squared on 4 tau. Okay, so there's a good reason why I'm doing this. So what we really want to look at are heat kernels, right? So we want to build a heat kernel. So we want to look at fundamental solutions for this, right? So the fundamental solutions for positive time also has to satisfy these equations. So I'm going to give you now the fundamental solution. Of course, we can try and derive it, but that's quite cumbersome. But the thick and thin of it is that we've reduced trying to compute the fundamental solutions to just real variable analysis, right? So we just need to do it for each lambda. We need to solve a real variable equation. That's really the power of taking a Fourier expansion, and also that's a luxury that we have when we have self-adjoint operators, right? You can just look up some tables or whatever. People have been thinking about this stuff and solved it, a very long time ago. But the end game is that we can explicitly write down the solutions for this. So when lambda is positive, we define lambda k1 tau t prime equal to just the tilde, right? So this is t tau t prime. And when lambda is negative, when it has to take that particular form, when it has to solve this eigenvalue equation, we have k lambda 1 tau t prime. So the first parameter is actually this fella over here, but we take a negative lambda now. And of course it doesn't matter because the lambda squares anyway, so whether we use a negative lambda or a positive lambda, it doesn't matter, but just for sake of impression, just let's leave it at that. And the error term now, or the term to produce this lambda out the front, is precisely this, right? T prime, and then we have the complementary error function of t plus t prime divided by square root 2 tau minus lambda square root tau. Okay, so where the complementary error function, so where c of x is a bad number to use, y, or maybe s, I'll write s here, we haven't used s so far, is the normalized integral, is this following normalized integral. S to infinity of e to the minus psi squared d psi. Okay, so unfortunately, you know, we can't spend too much time doing these elementary things, checking that. I mean, you have the equation here, so you can just differentiate this and you can check for it, right? You can check that this produces the solutions that we want. So now I'm going to give you the kernel. So the kernel, the Schwartz kernel, for e to the minus tau Laplace 1 is then the following. So it's k1 tau t prime, oops, maybe I'll put the variables here like this, tx t prime x prime is equal to the, well, maybe that. So this is equal to the sum over lambda k lambda of the 1 tau t prime phi lambda x prime adjoint tensor phi lambda of x. Okay. So is everything okay so far? That I haven't introduced any typos, or there's no squares missing or anything like that that someone observes, right? I mean, of course, I don't expect you to check the answer, but yeah. Okay, so let's now think about the operator lambda 2. So we do the same tricks here. So what do we have here? So this, now we're looking at lambda partial tau plus lambda 2 u tau t equals 0, and we have u tau t x equals the sum u lambda tau t phi lambda of x, which is in the domain of lambda 2. Sorry, I don't know why I keep calling the Laplacian lambda. It's delta. The eigenvalues are lambda. Okay, and so through a similar analysis, we can check that this occurs if and only if u tau t 0 is 0. But now for lambda, I mean, it swaps around, right? This is really a complementary boundary condition, right? The adjoint really is at the level of the complementary boundary condition. And now, of course, we have the because we're acting via the adjoint, we have negative lambda t plus lambda u lambda tau t 0 is 0 when lambda is positive. Okay? All right. So now now we want to think about the heat kernel again. So for lambda negative, same. So so this is the same as for before, but with the signs changed, right? So k lambda 2 tau t prime is equal to k tilde negative lambda 1, well, actually we could put real variables in there, so it doesn't matter, tau t prime. Okay, and for the positive eigenspaces, what we have is actually k lambda 2 of tau t prime is equal to k k1 lambda, k1 tilde lambda of t tau t prime minus lambda e to the lambda t plus t prime of the same error function of t plus t prime on 2 square root tau plus lambda plus move to the next line. Plus lambda square root tau. So actually I lie. I mean, I think here we had a negative, right? So in the error function for this we had a negative. So actually if you compare the two expressions, you can see that this is actually the expression for the first one, but with the negative lambda. Okay. All right. And so then this leads to, so then as before, we have that the full kernel tau t x t prime x prime is equal to the sum over the k tau t t prime phi lambda x prime dual phi x. Good. Good. So so this is the, well, I shouldn't say as before, similar to before. Is the heat kernel, is the Schwarz kernel, the heat kernel I should say. It is a Schwarz kernel, but e to the minus tau plus 2. All right. So now what can we say? Okay, so now let's write down a proposition. So for tau sufficiently small, so I should say tau sufficiently small, or I should say as, more precisely, as tau to 0 asymptotically, there exists some constant such that for all tau x, tau prime, x prime in this, yes, it's k2 lambda. Okay, so so whenever we're in the cylinder, we have that, oh dear, maybe we should write, since we're dealing with, yeah, okay, since we're dealing with the, I'm sorry, I've started writing partial m, but really we should be writing sigma, right? So we started off with a manifold sigma, and now we're looking at the cylinder over sigma. So I'll change that in the notes, but let's do it properly from here on. So really the partial m is the, of course, partial z is the sigma. So, but I've been writing partial m before, so you can change that to sigma, right? Okay. So what do we have? We have that each heat kernel tau t x t prime x prime. So this is the absolute value where we just take the we're taking the absolute values of the eigenvalues also, or the eigensections also, right? And so this is really a uniform bound. Tau negative a half n plus 1 e to the minus t prime on 4 tau. So in particular, ki tau t x t prime x prime decays to 0 exponentially as tau tends to 0, as long as yes, n is the dimension here. Yeah, n is the dimension of I should say this is, it's actually the dimension of the sigma. That's why we have a +1, because we're in Z, and Z is n plus 1 dimensional. Okay. Okay. As long as t and t prime are different, right? Of course, if t and t prime are the same, the exponential factor disappears. So let's have a quick look at a proof sketch. Of course, we can't get into the nuts and bolts of it. A lot of these proofs involving heat kernels are very cumbersome, so you want to maybe do them once in your life and never really do them again. Okay, so since so this is really the error function. Dx is bounded by negative e to the x squared. We have that the ki lambda tau t prime is of course bounded by e to the minus lambda squared on tau divided by pi tau to a square root plus 2. So this is just a calculation that you can do just from the definitions that we have, divided by tau, sorry, on the square root of pi. And this is actually, and this is weighted by e to the minus tau minus t minus t prime squared on 4 tau. I have the square here. I've missed the square. I'm sorry. There's a square there, right? Okay. So then we have that ki t tau tau t x t prime x prime is less than or equal to what? This is going to be less than or equal to 3 on 2 root pi tau. Constants don't really matter, of course. The sum e to the minus lambda squared tau on 2. And now we have the phi lambda x prime squared plus phi lambda x squared, all multiplied by e to the minus t prime squared on 4 tau. Okay, so now the main thing is you can see that we need to bound this internal part by some sort of nice, well, by really the tau to a negative 1/2, right? So so that really comes from so what is this? So before we looked at the traces of heat kernels. So actually the thing that we have in the middle here, the e to the minus lambda squared tau on 2 weighted by the phi lambda x prime squared and also the x, these are really the traces of the heat kernel for e to the minus a squared tau, right? So what am I saying? So the trace of e to the minus tau on 2, say, a squared. So for this operator, so the trace of this is actually just lambda e to the minus lambda squared tau on 2 phi lambda x squared. Well, okay, we have to integrate that, right? So I should really say that the trace of the heat kernel, right? So the trace of the kernel of e to the minus tau. What's a good notation? So the trace of the kernel, bold, maybe I'll write bold kxx, is this, where kx y is the heat kernel for e to the minus, sorry, I'm missing factors here, I'm sorry. There should be a tau here, tau divided by 2. So where this bold k tau txy is the heat kernel for tau a squared, right? So a is a self-adjoint operator, so a squared is also a self-adjoint operator. It's a differential operator on a compact manifold, right? For this on sigma. Okay, this is, which is a compact manifold without boundary. So actually, there are well-known heat kernel estimates. So since sigma is closed, or I should say, emphasize compact without boundary, heat kernel, and I should say, and a squared is a differential operator of order 2 on E sigma, which is self-adjoint. So in particular, it has domain H2. We have asymptotically, as tau tends to 0, we have the trace of the k tau xx is bounded by some constant tau to the negative n, well, negative n on 2. Okay? So then the estimate follows. The required conclusion then follows. Okay, so I should maybe give a reference for this, right? Sorry. I should maybe give a reference. CF, say, Attia, I think there's only one such paper, Attia Bot Patodi. Okay. All right. How are we going with time? Good, we're doing well for time. So what does this proposition tell us, right? So the importance of this proposition is that it tells us that what happens off the diagonal, right? So what happens away from the diagonal for the heat kernel expansions, for the heat kernel of this, now we have a cylinder over a cylinder, right? That's where we're really looking at this heat equation. So it's saying that when we're away from the diagonal in the transversal direction, in the first cylinder that we have exponential decay, so the contribution is going to be asymptotically small, right? So this, and this is a continuing theme. So this, so let me just write this down. So this proposition says that of the diagonal t prime in R plus cross R plus, the contribution is asymptotically small. Okay. So now we persevere to understand the kernel on the diagonal t equals t prime. That's where the interesting information is kept. Okay, so since we're interested in well, the trace of e to the minus t, tau plus 1 minus the trace of e to the minus tau Laplace 2, which, so the trace is actually a functional on this space, right? So on the space of trace class operators, so we can write it like this. So you can check this if you like. Okay. So now this tells us that we can try and look at the difference between the kernels of the operators. So we let the kernel, the heat kernel of 1, 2, tau t x t prime x prime equal to k1 tau t x prime minus the kernel of tau t x t prime x prime. Good. And define. So now we really only consider the kernels, right? So the traces. So we let k of tau t at x be equal to the trace of this fella on the diagonal. So tx tx. Okay. So let me just get a little breather. Okay. So for just the sake of notational simplicity, so let's say for the sake of notational simplicity, we let the signum of 0 equals to plus 1. That's really cheating. I mean, the signum of 0 should be 0, but anyway. And then actually we can do a calculation, and through calculation, which we're going to omit because the tough get going when the going gets tough. So it would be too much of an effort for us to calculate this, and it takes away from, I mean, I don't think we gain anything by sitting around calculating these things anyway. So what we get is that this object that we've defined is the signum of the lambda, and now we have negative e to the negative lambda squared tau multiplied by e to the minus t squared divided by tau, divided by, so big brackets here, pi t to a half plus modulus lambda. I really hope I haven't made any errors copying this down. If so, I will fix it on the sheet, on the lecture notes. Sorry. Of c tau on square root tau plus modulus lambda square root tau. And it's weighted by phi lambda x squared. Move this. Phi lambda x squared. Good. And so actually that's good, because now we can write it in terms of a derivative, right? So this actually is d dt of a half e to the 2 modulus lambda t of t on square root tau plus modulus square root tau. Ran out of room. Modulus of this squared. Okay. So now we integrate in t and x. So integrating in tx, so that's really recovering now. So that's really the trace, right? So we get that, so this is really the trace of the difference. So we get k tau, which is equal to 0 to infinity sigma k tau t x d mu x. Sorry, this is d nu, isn't it? I think we had the measure nu on the boundary. dt. This is equal to negative lambda signum to c modulus lambda tau, square root tau. And so what? And so we differentiate now in tau. So if we differentiate in tau, we get that this is 1 on square root 4 pi tau sum over lambda lambda e to the minus lambda squared tau. Okay. So now the other thing is, note that the ERF-C function evaluated at 0 is equal to 1. And since we sum over lambda counting multiplicities, the k tau is what? So it's equal to this this signum so I'm gonna peel away the 0th eigenvalue, right? So then the first part that we pick up is the negative of the dim kernel of A on 2. So this is why I organized my signum. I took the note, I just cheated and assumed that the signum of lambda at 0 was 1, so that we don't lose that, right? So, and then now I have the sum over the non-zero part, so the non-zero eigenvalues of what? Of ERF C modulus lambda square root tau. Okay. Oh, sorry, there's a signum missing. Sorry. There's a signum here. Ah. Okay. Okay. So, as we noted before, so also we note that the Earth C of S is less than 2 on root pi of e to the minus s squared, and therefore what do we have? We have that firstly k tau goes to negative a half dim kernel of A, which we define as Atiyah Patodi Singer did to be maybe this calligraphy H, some sort of H that's different from the normal H because we're using that for the metric, as tau goes to infinity. And k tau plus a half h is bounded by this quantity, lambda non-zero, e to the minus lambda squared tau, as again tau goes to infinity. Okay, that's not really saying much more than what we said before. And k tau is bounded by some constant tau to a negative a half n as tau goes to 0. So what's the point of all of this? So all of this then gives us that if we integrate the quantity k tau plus a half h with t with a power t to the s minus 1 d tau, this is finite. Okay, so it's just to guarantee the finiteness of this integral. And this is, so okay, I should say what this is for. So this is for complex S with the real part of S sufficiently large. Okay, so why are we doing all of this? So remember, we want to try and connect all of this to the eta invariant, right? That's really the point. So now let's use integration by parts. So using integration by parts and expression for the derivative, we get that this integral is k tau plus half h, or this fancy h I tried to write, tau to the s minus 1 of the d tau is, okay, so again, this is a calculation, and you know, I'm not gonna go through it, but this is equal to now negative gamma. So this is the gamma function of s plus a half divided by 2s square root of pi, some lambda non-zero, signum of this divided by this 2s. So what is this? This is exactly negative gamma s plus a half over 2s square root of pi, the eta function evaluated at 2s. Okay, so the eta, the big pi, that's not a pi, that's a gamma. This is the gamma function, right? So this is the gamma function applied. So, okay, maybe I say where the gamma is the gamma function. Okay, so maybe I'll include what that is in the notes. All right, so we have still 15 minutes. So what can we do in this time? So now, okay, so let's just make a remark. So of course, a lot of these calculations have been, you know, I mean, it seemed like magical, but this was a serious endeavor for Atiyah, Patodi, and Singer. And this also shows how for these first order operators and for the study of this eta function, what's really important is a boundary condition that's not local, right? So the boundary condition that we equipped for this operator where we did all of these calculations is non-local in the sense that it's given as a spectral sum of eigenfunctions of the associated operator, namely the operator A. So a boundary condition is local if when we multiply by, say, a compactly supported smooth function, it maps us back into the domain of the operator. I mean, there are different definitions for what it means for, there are different ways to understand and formulate what it means for a boundary condition to be local, but a particular fact about all these different ways of thinking about local boundary conditions is that multiplying by compactly supported functions preserves the domain of the operator. So for a non-local boundary condition, this is not always the case, right? So here, if I multiply by a compactly supported smooth function, say on the domain of the operator that I'm looking at, so D nord APS, there's no guarantee that if I now restrict this to the boundary, that I'm going to remain in the spectral subspaces, right? Because the compactly supported smooth function up to the boundary will also take a value. So the boundary condition will then be the restriction of that function multiplied by the original restriction. And of course that's guaranteed to be in DOM D max, but there's no guarantee that, so it's going to be in the check space, but there's no guarantee that this is going to now satisfy this nice spectral condition. And in fact, in the Atiyah, Patodi, Singer paper, they mentioned this. They mentioned that their whole enterprise of trying to build or find an index theorem for the boundary case was delayed by almost 10 years because they were trying to look for local boundary conditions. If you're looking at second order operators, typically like Dirichlet or Neumann, these are local boundary conditions. And so they anticipated and expected that the boundary condition that connects to the eta invariant should be a local one. But then they were able to prove that there are topological obstructions that don't permit this, right? So it's provably false that you will get the nice kind of boundary conditions that allow you to understand the eta from a local boundary condition. So this is somehow why the ability to decompose the check spaces. So this is really important for the first order operators. It's unclear to me how important this is for higher order operators, but for first order operators, this is extremely important because the right kind of boundary conditions, the important boundary conditions, at least for index theory, has to come from non-local considerations. And there we have to really understand the check space in terms of an associated operator on the boundary that allows us to do spectral cuts and decompose the check space in terms of the spectral information of that operator, right? So the theorems that we had really early on allowed us to understand this in terms of the Calderon projector, but the Calderon projector is not necessarily going to be of the form where we can write it in terms of some operator that exists on the boundary itself, right? This is why it's so important for us to be able to decompose the check space in terms of an associated adapted boundary operator on the actual boundary. Okay, so having said all of that, let's think about how to get an index formula. So we're on an infinite cylinder, so we're not going to look for an index formula there, so we have to relate things back to compact manifolds. So let's make a start on this and continue next time. So index formula. So what do we need for this? So let's look at the setup. So now let's return back to the setup where M is compact with boundary. With boundary. And we have E, H, E maps to F, H, F. Sorry. These are Hermitian bundles. And we have D being an elliptic differential operator of order 1. Elliptic. And we have to further suppose some things, right? We need this manifold now to apply the theory that we already have. We want it to be product at the boundary. And U rho is diffeo to Z rho, which we wrote before as up to rho cross partial M, such that, so we want the operator now to take a nice form. We want to take it a product form near the boundary, plus A, inside U rho with a self adjoint. Okay, so that's the situation that we want to look at. So of course now we could always just consider the model problem as we've already done. So from before, we know that H check space of this D is equal to H check space of the operator with D naught, right? So just this model operator. Okay, so now let DAPS be the operator act as Dmax with domain, so I should just say equals Dmax with domain dom DAPS equal to U in dom D max, such that the restriction now lands just move this a bit in BAPS of A, which is what? Which is exactly the U in dom D max, such that the restriction lands in chi plus of A little a acting on H half partial ME, where A is always equal to the minimum of the modulus of the two eigenvalues, right? Okay, so we also now know that this is a Fredholm operator, right? So we also know that BAPS of A is elliptically regular, and hence DAPS is Fredholm. Okay, so now let's we have two new Laplacians now. So now let's let L1 equal to dAps star dAps and L2 equal to dAps dAps star. And so we can now write the index of dAps, which we know is a finite number, okay? Because it's a Fredholm operator, as dim kernel dAps minus dim kernel dAps adjoint is equal to what? This is equal to dim kernel dAps dAps, 1 second, dim kernel dAps dAps star. Yes? I've given the domain here, right? So this is really to say that it acts as Dmax. If you like. Yeah. Okay. Yeah, that's probably a better way of writing it. All right. So we have this, and now we can use the tools that we have from before. So this is now going to be what? This is going to be tau L1 minus the trace e to the minus tau L2. Okay. Delta was the D naught APS, right? But now we're looking at D on a compact manifold. Okay, so yes, thanks for that. That's an important difference here. So now we're no longer on the cylinder, right? Because we want this finite index. So maybe we'll just go up to the definition of the next thing. So let M tilde be the double. So now we're going to double the manifold over the boundary, right? So this is the double of M. The double of M since D is product near partial M, the operator doubles. That means the coefficients are smooth, right? So the only real, I mean, of course we can always double an operator, but then we're only guaranteed that the coefficients are continuous across the boundary. But if the boundary has no mean curvature, actually no, you need high derivatives also. So it really needs to be product, or product is sufficient at least. I don't want to make a precise statement here because I can't remember it. But as long as it's product, what we end up with are smooth coefficients when we take the double of the operator, right? So so we get an operator that's smooth across here. The operator doubles to D tilde now in so God. So the operator also doubles now to so the operator now doubles to, so the bundles also double. So I'm going to denote the doubled bundles by E tilde or F tilde. So this is now an elliptic differential operator of order 1 on the double. So now we know from before, again, from before, we know that d tilde has a unique closure, i.e. d tilde min equals d tilde max, since m tilde is compact with the boundary of m tilde being empty. Okay? And in fact, their domains are going to be H1. With abuse of notation, we write d tilde in place of d tilde closure. Okay? Now we define L1 tilde equals to d tilde star d tilde, and L2 tilde equals to d tilde d tilde star. Okay, so let's just leave it at that. So what we want to do, we want to now, so next time consider the trace also of e to the minus tau L1 tilde minus e to the minus tau L2 tilde, right? Which is really now, this is going to be the index of the d tilde on the closed manifold, right? So we already know that it has an index because it's a Fredholm operator. But the point is that we need to consider both the L1, L2, and the L tilde, and the L1 tilde and the L2 tilde. We need to consider all of these things simultaneously because the geometric data. So we have a geometric term in the index formula and we have a boundary term. So the boundary term, so this is really for next time, the boundary term will be visible from considering this object here, and the geometric term will come from considering this object here, right? So we'll see that next time.